Today we are going to do literally what it says on the screen and talk more with differential equations. We have done some pretty basic stuff, but now we're going to do a little bit more with some applications. Before we get into that, what I want you to do, pause the video, solve these really quickly if you can, and then come right back, see if you get the same thing. But these are just some basic differential equations, no applications yet. And so what we want to do here is we want to solve them for y. Remember, we want to get our, well, not our particular solution because we don't have initial conditions, but we want to get our general solution. So again, remember when we start these, you always want to get your variables separated. So I'm going to go ahead and multiply both sides by dx right here. So I've got dy is equal to x plus 2 dx. Then I can integrate both sides. Is equal to the integral of x plus 2 dx. And now when I write it like this, it's understood that the dx in the integral encompasses the whole thing without using the parentheses. So then I end up with y is equal to x squared over 2 plus 2x plus c. And this one works out really well that y is already solved by itself. So that one is already done. Let's look at this other one. We're going to start it out the same way, but unfortunately, I end up with y plus 2 dx. Well, this is a problem because I have y on the same side as x. So I'm going to go ahead and divide that over and make that dy for y plus 2 equals dx. And now I'm at the point where I can easily integrate both sides. This is going to be the natural log of the absolute value of y plus 2 is equal to x plus c. Okay. Again, to get the general solution, we have to get y completely by itself. So in order to get rid of the natural log, I have to raise e to the power of both sides. So I've got y plus 2 is equal to e to the x plus c. Now remember, well, I don't know if we've had a video about this just yet, but whenever we have this scenario right here, where it's e to the x plus c, this may go over here. E to the x plus c is the same thing as e to the x times e to the c if we're using our exponent rules. Remember how if the bases are the same, you just add the exponents? Well, technically this whole thing right here, because I don't know what c is, this in and of itself is some constant that we don't know. So what we are allowed to say is instead of e to the x plus c, I can just call this c e to the x because I'm saying that this whole thing is c as a constant. Okay, so now anytime you have to undo the natural log by raising it to the power of e on the other side, you're going to take that constant and then bring it out front to make it c e to the whatever. In this case, it was just c e to the x, but you would do that anytime you see this. So now I've got the absolute value of y plus 2 is equal to c e to the x. And then because of your initial condition, that will help you determine, do you want the positive or do you want the negative? I can go ahead and say y plus 2 is equal to c e to the x, and y is equal to 2, nope, I'm sorry, my bad, c e to the x minus 2. And that c right here is going to be positive or negative depending on whatever your initial condition is. So you would have to know that, though, for sure in order to figure out what c is. Okay? That's a real quick version of that. Let's do one more. Again, I would go ahead and try this one on your own. Now, this time we are going to get the particular solution because they're giving you the initial condition that y of 1 is 2. Pause the video, try it on your own, see if it works. If not, come right back, keep on watching. Okay, so hopefully you pause it, now you're back. So I'm going to get y prime by itself. So 2xy prime is going to be equal to natural log of x squared. Y prime equals the natural log of x squared over 2x. So then, let's see, I'm going to rewrite, I don't have dy or dx here, but I can rewrite y prime as dy dx. So that way now I have natural log of x squared over 2x, multiply both sides by dx. So dy is equal to the natural log of x squared over 2x dx. And at this point, I can integrate. So y is equal to, now this one, we're going to have to do a u substitution for this one. Hopefully you guys can identify it really quickly, but if not, that's okay. Here I'm going to erase the y for just a second. So for this situation, I'm going to say u is equal to x squared and du is equal to 2x dx. Okay. Let's see, does that work? If I did that, oh, but the 2x is in the denominator, and okay, well, you know what, guys? Sometimes this happens. So let's try this another way, okay? So my first initial thought was to say, okay, well, let's just make x squared u. But when I took the derivative of that, the 2x was in the denominator, but the dx is in the numerator. That's not going to work. Let's go back. So when in doubt, when you're doing a u substitution and it doesn't work, go back and try something else, okay? So, what I know, though, is that if I have the natural log of x squared, well, technically, this is the same thing as 2 times the natural log of x over 2x. That's when I use my log properties to bring it to the front, okay? And then dx out here. So if I do that, well, then the nice thing is the 2's cancel. So now I'm left with the integral of the natural log of x over x dx. Now I can do an easier u substitution. I can say u is equal to the natural log of x, and then du is 1 over x dx, which I do have right here. That works out much better. Again, though, I don't know that I would have noticed that right away because I saw the natural log of x squared. I was like, oh, that's my u, okay? Again, this happens. Try it. If it doesn't work, go back and try something else. There's nothing wrong with that. So now I can rewrite that one as u du, and so this becomes, I already know that this side is just y, is equal to u squared over 2 plus c, but remember, u was the natural log of x. Just because I want to keep that initial condition nearby, I'm going to scroll up, grab this, bring it down. Here we go. Okay, let's go over here. Oops. Let's go over here. So y is equal to u squared, so the natural log of x squared over 2 plus c. Okay, now here I can't use a log property to rewrite that 2 because the entire natural log is being squared, as opposed to earlier just the x was being squared. When just the x is being squared, then you can bring it out front. You cannot do that here. Okay, so I'm going to plug in my initial condition. 2 is equal to the natural log of 1 squared over 2 plus c. And so now, natural log of 1 we know is 0, so that works out to our 2 equals c. So then y is equal to the natural log of x squared over 2 plus 2. Boom, done. That is the particular solution to the differential equation up at the top with this specific initial condition. If I had a different initial condition, it'd be different. Okay, so solve for the general solution for the following situation. The rate of change of y with respect to time is directly proportional to the value of y. Okay, so I've got dy dt is equal to k times y. This is a very common scenario where now instead of differentiating with respect to x, just our regular independent variable, now we are differentiating with respect to time. Okay, now I don't actually know what the question here is. They're just telling me that I know that y is directly, or the rate of change of y is directly proportional to the value of y. So pretty commonly we'll use the letter k to represent our proportionality constant. I don't know why we typically use that letter. Well, we don't want to use c because c is what we use for our constant of integration. So we're going to use k for the proportionality constant. So I've got, yet again, I'm trying to find the general solution, which means I need to solve for y. So here, I'm going to say dy over y, because I'm going to divide both sides by y, is equal to k, and then I'm going to multiply by dt. Normally I multiply by dx, now I'm going to multiply by dt. Okay, so dy over y becomes the natural log of the absolute value of y, and then this becomes kt plus c. Now remember, instead of an x, I'm using t, so that's why this is a t, and k is just a constant, okay? But it's our proportionality constant, so that's why I leave it as k, and then I still have plus c for my constant of integration. Okay, so now I just need to solve for y, so the absolute value of y is equal to e to the kt plus c. Now remember from earlier in the video, when I have this c right here, I can rewrite that as capital C e to the kt, and then here I can just drop the absolute value because that's going to change depending on my initial condition. Okay, so now so the general solution for this situation is y equals c e to the kt. This is a very, very common differential equation, and it's very, very helpful if you already have the solution memorized. So you don't have to. If you wanted to, you could work it out every single time. That's perfectly fine. But if you have it memorized, it's going to help you out in the long run. Okay? Now, some of you might notice this looks a lot like A equals P e to the RT from back in your pre-cal / algebra 2 days, okay? These are one in the same, okay? Depending on what your rate of change is, your proportionality constant, aka your interest rate, okay? That's going to affect what your interest is, or well, your overall interest plus principal is, okay? This is our exponential growth formula as well. Well, I say it's exponential growth. That's true as long as k is greater than 0. It would be decay, when k is less than 0. All right? So let's look at some specific examples. Oh, actually, nope, just kidding. Sometimes you're going to have different phrases. So whenever you see something like W is directly proportional to Y, you would write that as W is equal to K, your proportionality constant, times Y. Sometimes they're going to tell you that W is indirectly proportional to Y. Okay? If that is the case, W is going to be K divided by Y. All right? They're indirectly proportional. Every now and then, not a lot, but every now and then you see W varies jointly with X and Y. Again, this one we don't use it as much as we do these other two up here, but if you did see that, you would say W is equal to K, X, Y. Okay, so the reason why I'm telling you these things is a lot of times that we're just going to give you a sentence or a phrase, and you're going to have to write out the differential equation on your own and then turn around and solve it. So these are 3 very common ones. Well, 2 pretty common ones, and then a third like somewhat common. Okay, so let's see. Applications. Oh, yes, this is the good stuff. The rate of change of Y is proportional to Y. The rate of change of Y is proportional to Y. To write out the rate of change of Y, remember we would write that as dy dt. This is the rate of change of Y. Is proportional to Y. So is proportional to Y. Okay? When t is equal to 0, y is equal to 2. When t is equal to 2, y is equal to 4. What is the value of y when t is equal to 3? Ooh, so these 2 things right here look like they're pretty valuable. This one specifically is my initial condition because t is equal to 0. And this one is still another condition. It would be an initial condition if it was the only one that I was given. But because I'm told what's happening when t specifically is equal to 0, this guy right here is going to be my initial condition. Okay, well, I could go ahead and solve this whole thing out just like I did before, but we've already done this problem. We did this just a second ago. I know that the solution to this is y equals c e to the kt. And since I have that memorized, I don't have to go through and keep reworking it every single time. So that's why it's really beneficial to have that memorized, okay? So now, let's see, if y is equal to c e to the kt, let's plug in some of these conditions here so that way I can figure out, excuse me, I had to yawn, my bad. I'm trying to figure out if I plug in a 3 right here, what is my value of y? But I can't do that until I know what c and k are. I guess it's not going to help. So let's solve for some of these here. So I know I've got the point 0, 2. So let's plug that in. You know that you're going to get 2 when c, e, k times 0. Okay, well this works out really nicely because e to the 0 is 1. So 2 equals c. So now I've got y equals 2 e to the kt. So we're a step closer, but I still don't have k yet. All right, well, luckily we have another point. So now when I plug in the point 2, 4, maybe that will help me solve for k. Essentially, it's like a system of equations that I have here, sort of, kind of. So 4 is what I get when I plug in 2 e to the k times 2. So divide by 2, so 2 equals e to the 2k. I still need to solve for k, so to do that, I'm going to go with the natural log of 2 is equal to 2k, because that's how you undo an exponential using our exponential properties from Algebra 2, I believe. Take the natural log of both sides. And then, let's see, natural log of 2 over 2 is k. Perfect. So now my equation is y equals 2 e to the natural log of 2 over 2 times t. Because remember, I found c was equal to 2, so I plugged that in, and k was natural log of 2 over 2, so I plugged that in right here. Boom, done. So, well, I say boom, done. This gives me my final equation. I'm still trying to find the value of y when t is equal to 3. So y equals 2 e to the natural log of 2 over 2 times 3. And here you could either leave your answer like this, or if you wanted to plug this into your calculator, y is 5.657. So that is the answer. What is the value of y when t equals 3? All right. So that one was an application problem, but it wasn't a too difficult one. It wasn't like a big application. Let's look at another one. Okay. Suppose an experimental population of fruit flies increases according to the law of exponential growth. We had 100 fruit flies after the second day of the experiment and 300 after the fourth day. Approximately how many flies were in the original population? Ooh, okay. So we're actually trying to find our initial condition. All right, so we know, here's what we know. An experimental population of fruit flies increases according to the law of exponential growth. Well, the law of exponential growth is y equals c e to the kt, and we know that this value of k is going to be greater than 0, okay, because this whole thing is going to grow. All right, so then let's see. Actually, it should be greater than 1. Did I say greater than 0 earlier? That's wrong. Let me go back here. Let me go back. Exponential growth. Oh, Murphin. That was a boo-boo on my part. Greater than 1. Less than 1. Okay? Because if it's decay, yeah, you could have a half and it would get smaller. Oh, silly me. My bad. All right. Or is it 0? Now I'm totally confused here. Hang on a second. So sorry for that brain fart. It's 0. What am I? I was right the first time. Don't second guess yourself, guys. That's what the lesson of the day is. Okay? Exponential growth. Okay? That's going to be bigger than 0. All right. My bad. Anyway, so I know that I have fruit flies. Let's see. There were 100 fruit flies after the second day. So after the second day, so I have this data point. So after day 2, there were 100 and 300 after the fourth day. Okay, so now let's see here. I'm going to use both of these data points because I need to figure out, I want to know how many flies were the original population. So that means I need to know how many flies when t was equal to 0. But again, to do that, I need to find k, I need to find c. All right, so let's just plug in this first data point. So I know 100 is what happens when I have c e to the k times 2. Well, all right, that doesn't really help me out like it did in the last problem, because last time this just canceled out to a 1, and I was very easily able to find c. But I can at least get c by itself here and make this 100 over e to the 2k is equal to c. All right, so that's a good step. So now I've got y equals 100 over e to the 2k times e to the kt. It's not pretty, but you know what? We're gonna make this work. And I realized that I could. I understand that I could clean this up a little bit with my exponent rules. But for right now, I'm just gonna hold off because I'm gonna wait and throw some more numbers in and see if that helps me out just a little bit more. Okay? So I realize some of you are like, clean that up, make it prettier. Just hang on a second. All right, so now I'm going to plug in this term over here. So 300 is equal to 100 over e to the 2k times e to the k times 4. Okay, again, I just plugged in this data point. So now let's see if I can clean this one up just a hair bit here. So I've got 300 equals 100. Now I have e to the 4k, e to the 2k. Again, e to the 4k, e to the 2k. Using your division rules for exponents, this guy divided by this guy, I subtract my exponents, and this becomes e to the 2k. All right, because you would have e to the 4k over e to the 2k, subtract your exponents. All right, so now I need to solve for k, so I divide by 100, so 3 equals e to the 2k. Natural log of 3 is equal to 2k. So the natural log of 3 over 2 equals k. So now my equation is y equals 100 over e to the 2 times natural log of 3 over 2. Because remember, now that's k. This is k, so I can plug it in here. I can plug it in there. Again, I can clean this up, and I will. Just bear with me for just a little bit here. And then, so this is my value of c times e to the k, natural log of 3 over 2t. All right, let's clean this up. I can sense that you guys are on panic mode right now. 100 over 2 times something to the 1/2. Those cancel out. So e to the natural log of 3 times e to the natural log of 3 over 2t. Okay. E to the natural log of 3. That cancels out. So y equals 100 over 3 times e natural log of 3 over 2t. Now technically I could do a little bit more here, but you know what? We've cleaned it up quite a bit just by getting rid of that part. I think from here we're okay. We want to know how many fruit flies were in the original population. To do that, I just plug in a 0. So y of 0 is 100 over 3 e to the 0, essentially, because natural log of 3 over 2 times 0. E to 0 is 1. So the initial fruit fly population was 100 over 3, which is 33.333 flies. They didn't tell us what to round to, so this just says approximately. I mean, we would probably just say 300 or 33 flies, okay? You can't have a third of a fly, but it just works out that the math looks that way. So they would tell you though specifically what they want you to round it to. They didn't this time. How lovely, how convenient. Okay, let's try another one. Let's see. Actually, you know what? This one works out very similarly to the last problem, example 4. So I will have this worked out on Canvas, but I'm gonna save some time on this video and just go ahead and skip over this, but I will have it worked out on Canvas whenever you go back and look at that. Also, it's in your textbook. Okay, let's talk Newton's law of cooling. It states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium, meaning the space around it, okay? So for example, you pull a cake out of the oven and your kitchen is 75 degrees Fahrenheit. Let's write an equation to represent that. So Newton's law of cooling states the rate of change in the temperature. So to write that equation is very simply for temperature, I'm going to use Y for now, because if I use T, I feel like that's going to be confusing. So dy dt. So this represents the rate of change of the temperature is proportional. Okay, now they didn't say directly, but no, anytime they don't say the word directly, it's implied. Okay, so is proportional or is directly proportional. So that means I need my proportionality constant to the difference between the object's temperature and the temperature of the surrounding medium. Difference meaning subtraction. So the temperature of the object, so Y, and the surrounding medium. So in this particular situation, it would be 75 degrees. Oh, I just want to write 75. Okay. In general, you could write a capital M right here to show that it is the, the general form of this, of Newton's law of cooling. So this is another thing that you're going to want to have memorized. So when they tell you that something cools using Newton's law of cooling, this is what they want you to use, okay? The temperature, or the rate of change of the temperature, is directly proportional to the difference between the object's temperature and the surrounding medium. And this makes perfect sense, okay? If you think about it, if you pull a cake out of an oven and your kitchen is 75 degrees, okay, that's going to cool at a rate that would be very different than if you pulled your cake out of the oven and the kitchen was at 100 degrees. Your cake would not cool down as quickly at 100 degrees in the kitchen than it would at 75 degrees in the kitchen. And so it's proportional to the difference between the cake's temperature and the temperature of the surrounding medium. Okay? Let's look at an example here. So let Y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant of 60 degrees. That is a cold room. If the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? Okay, so let's start with Newton's law of cooling. So dy dt is proportional to the temperature of the object, which we don't know, so Y, and the temperature of the surrounding medium, which we do know it's kept at a constant of 60 degrees. Okay. If it cools from 100 to 90 in 10 minutes, how much longer to decrease to 80 degrees? So basically, I know that initially the temperature is 100. After 10 minutes, it becomes 90 degrees. I need to know how long or how much longer is it going to take for me to get to 80 degrees. Okay, so first I need to solve this equation here for Y. It's not as simple as exponential growth or decay, so I don't automatically know the answer to this. So I'm going to say dy over Y minus 60 is equal to k dt. I divided this to the other side and I multiplied by dt. Integrate. So this becomes the natural log of the absolute value of Y minus 60 is equal to k t plus c. So now from here, I want to undo the natural log. Now, another thing I want you to think about here, just because our rules dictate that when we take the antiderivative of this, I have absolute value bars. But let's think about this. The temperature of your object minus 60. So the temperature of your object, if your room is 60 degrees, the object itself cannot cool lower than 60 degrees. So technically here, if I wanted to, I could go ahead and change these from absolute value to parentheses, because I know that this term right here is going to be positive no matter what. Okay? I know I don't usually say that you should write over it, but hey, you know what? we're good. So now y minus 60 is equal to e to the kt plus c. But I know that I can make this y minus 60 equals equals c, e to the kt. And so y equals 60 plus c e to the kt. So then let's see here. I wanted to know how much longer to get to 80 degrees. Now another note here. We did not exponential growth. We did a Newton's law of cooling, and it solved to this format right here. If you'll notice, this looks very similar to the exponential growth or decay. It's just that you're going to add your surrounding medium to the outside. So if you wanted to just skip from here to that, unless they specify, you could do that. But for this one, it might be better to go ahead and work it out. Totally up to you. All right. So now, let's see. I need to solve for C and K so I can actually plug in the 80 to figure out how long this would take. So again, I'm going to use some of these data points I already had. So I've got y equals 60 plus c e to the kt. So I know that the temperature is 100 degrees when I, whatever this object is, if I pull it out of the oven or whenever I start this whole scenario, okay? So luckily, e to the k times 0 becomes e to the 1. So 100 equals 60 plus c, so c equals 40. Okay, good. So now I've got y equals 60 plus 40 e to the kt, because I just went ahead and plugged in the 40 for c. And so now I just need to solve for k. To do that, I need to plug in the other data point, because if I plug in the same one I already had, that's silly. So 90 equals 60 plus 40 e to the k times 10. Let's scroll down a bit here. 90 minus 60 is going to be 30 equals 40 e to the 10k. I'm going to divide by 40 on both sides, so that becomes 3/4 equals e to the 10k. Take the natural log of 3/4 is 10k. So k is equal to the natural log of 3/4 over 10. All right, so now I'm going to go over here, since I've got a lot of this space, equals 60 plus 40 e to the natural log of 3/4 over 10t. I need to know at what time or how much longer it'll take me to get to 80 degrees. So I already know that this is going to be 80. Okay, so I've plugged everything in, and we just need to solve for t. So subtract 60, so 20 equals 40 e to the natural log of 3/4, that's a 4 right there, over 10 t. Divide by 40 on both sides, so 1/2 equals e to the natural log of 3/4 over 10 t. You could have cleaned this up a little bit differently, and that's fine if you want to do that. I know that we'll get there eventually. To undo e, you take the natural log of both sides. So then the natural log of 1/2 is equal to, by taking the natural log of all of this stuff, basically the e goes away and I'm just left with the original exponent. So natural log of 3/4 over 10 times t. I'm just trying to isolate t. So I'm going to multiply by 10 over the natural log of 3/4 on both sides. Yeah, that's going to, it's over here. I'm just out of room. So I've got the natural log of 3/4 over 10 times the natural log of 1/2 equals t. So this answer would be, ooh, did I write that right? I did not. I did not write that correctly. You know what? I catch myself sometimes. That was silly. See how I wrote it by? I wrote it right over there. This should be 10 over the natural log of 3/4. I'm sure some of you guys were thinking that and screaming that at me, but I can't hear you. I'm sorry. Okay. This would take 24.094 minutes. This is if I went from from time is equal to 0 to 24 minutes, my object, I don't know what it is, would have cooled down to 80 degrees. But the original question was how much longer would it take? We have to be very careful with this. How much longer will it take? Well, it's already taken us 10 minutes so far, so it will take 14, roughly 15 minutes, 0.094 minutes longer for the object to reach 80 degrees Fahrenheit. Okay. That is all of our notes for today on the applications of differential equations. I have a worksheet for you guys for this particular set of notes that you're going to do. I also have the key for this handy, so that way you can try them and then also check your work. As always, if you need any assistance, Prof. Rob Bob, Calc Chat, Calc View, and Khan Academy.